Hi everyone, my name is Manojit Nandi, and this is my talk, Games, Algorithms, and Social Good, about the interplay between game theory, machine learning algorithms, and the AI for social good movement. First, let's do a review of what game theory is, starting with probably what is the most famous game in game theory, the prisoner's dilemma. So with the prisoner's dilemma, the story is as follows. The police arrest two members of a criminal gang for some crime and put them in solitary confinement, so the two prisoners cannot interact with one another. The two gang members cannot interact with one another. However, the police don't have enough evidence to prosecute them for a serious crime, and so they go to each prisoner and offer them a plea bargain. If you rat out the other prisoner and they stay silent, you will go free and they will get 5 years in prison. If you both choose to stay silent, you both get 1 year in prison. If you stay silent and they rat you out, you get 5 years in prison. And finally, if you both rat each other out, then you both get 3 years in prison. And one common idea in game theory is that we want to find this Nash equilibrium, which is not the optimal outcome, but it's sort of the outcome in which no player wants to change their action. They don't want to change their decision if you fix everyone else's action. So how do we find the Nash equilibrium for the prisoner's dilemma? Well, let's think about what happens from player 1, or criminal 1. If the other criminal chooses to stay silent, then you can either get a payoff of 0 years in prison if you confess and rat them out, or you get 1 year in prison if you also choose to stay silent. And since you really only care about yourself, you would want to confess, you would want to rat them out so that you get 0 years in prison rather than 1 year in prison. If player 2 chooses to confess, then what you'll want to do is you'll want to confess as well. If they rat you out, then you want to rat them out in return and get 3 years in prison versus staying silent and thus getting 5 years in prison. So no matter what player 2 does, player 1 will always want to confess. They'll always want to rat out the other person. And because this game is symmetric, the same payoffs occur for player 2 as they are for player 1, the same thing is true for player 2. No matter what player 1 does, player 2 will always want to confess. They will always want to rat out the other person. As a result, both players will want to confess, so the Nash equilibrium of this game is confess, confess. And the prisoner's dilemma is very popular because of this paradoxical outcome, that two individuals who are acting optimally in their own self-interest lead to the suboptimal outcome. These two prisoners are sort of doing what's best for themselves, and it leads to this outcome of 3 years in prison for the both of them. On the other hand, if you look at this game, you can see that there's a much better outcome in which they both stay silent. They both stay silent and they both only get 1 year in prison. And there's a lot of variations on this game. There's a lot of research on how to sort of shift the equilibrium from being confess to both staying silent. But that's not really what I want to focus on for this talk. And I want to talk about a different game instead. And that game is the Stag Hunt game. So the story of the Stag Hunt game is as follows. There are two hunters, and they have a choice of between hunting a hare, like a small rabbit, or a stag, which is a large deer. And the thing about this is that each hunter is skilled enough that they can hunt the hare individually, but in order to take down the stag, they both need to have decided to go hunt the stag together. And you can see it here in the payoff matrix, that if both hunters go for the stag, they both get a payoff of 5. On the other hand, if they choose to go hunt the hare, they get a payoff of 2. If one hunter goes for the stag and the other hunter goes for the hare, then the hunter who went for the stag gets a payoff of 0 because they'll fail to hunt the stag by themselves, and the hunter who went for the hare gets 2 because they got the hare. And if you work it out, there's actually 2 Nash equilibriums for this game. There's stag, and there's also hare. And the reason I really like the Stag Hunt game is because it shows the evolution of trust and value of communication. There are 2 Nash equilibriums, stag and hare, but stag is clearly the better equilibrium. It's the one that leads to the better outcome. But in order to get this better outcome, the two hunters have to trust each other. They need to communicate with each other. And so I think this is a game that has a very interesting moral in that the way to get the mathematically optimal outcome, even if both players are self-interested, is by trusting and communicating with each other. And I love that idea that oh hey, in order to get the best possible outcome, we need to trust and communicate with each other. That having these, that the solution requires us to do these things that are essentially good for all of us, and we need to have trust and communication. And I love that story more than the prisoner's dilemma's moral, which is just like, people doing what's in their best interest leads to disastrous outcomes. That's just dystopian future. But the Stag Hunt game shows us a future where people trusting and communicating to each other, opening their hearts to one another, that's how we win. That's how we get the best possible outcome. And that's sort of the theme I want to go for this presentation, is that how can we sort of achieve the mathematically optimal outcome by pursuing trust and communication and justice and fairness. And so, talking about trust and communication, I want to talk about this special sub-branch of game theory called cooperative game theory. Whereas regular game theory focuses on what the individual is doing what's best for themselves, cooperative game theory focuses on how do we build the optimal team of players. And rather than in cooperative games, the unit we focus on is sort of a coalition. It's a group of players. Whereas in a normal form game, we focus on the individual player themselves. In cooperative games, we care about the coalition. We care about the group of players. And the main idea behind cooperative game theory is we want to build a team of players to achieve some common outcome. We want to assemble a team of soccer players or football players that are most likely to win all the matches they come across. We want to build a team of Pokemon that are most likely to win the most battles, for example. And this idea of how we build strong teams and the theory behind it appears a lot in ensemble learning and machine learning. With ensemble learning and machine learning, you're either boosting or bagging a group of machine learning classifiers, such that you build some combined machine learning classifier that's very strong and robust and has higher predictive accuracy than any of the individual components to it. And the way it's done is by using this idea of boosting comes from this idea of cooperative game theory, that you want to build a set of models that, as you build your combination of models, your coalition of models, you're sort of covering the existing weaknesses. So that when you add model 2 in existence to model 1, model 2 covers the weaknesses of model 1. And more interestingly, and more recently, we've seen this ideas of cooperative game theory arise in this field of machine learning model interpretability and model explainability. Researchers have thought about how can we view this idea of feature attribution and model explainability as a cooperative game. And the idea here is that the features of the model are seen as players of the game, and the model's output is the result of the game. So the features of the models are trying to work together in order to get the best output for the model. So how does this work? Well, it uses this idea of Shapley values. And the key idea behind Shapley values is, so can we measure how much each player contributes to the team? You hear a lot about this idea of an MVP, the most valuable player, and the idea behind an MVP is that that player contributed the most to that team. And how can we thus mathematically formalize this idea of player contribution? Well, the heuristic here we're going to use is that if you remove that player from the team, and the outcome doesn't change, that player wasn't really useful at all. If the team would have won without that player, the player didn't really do anything. Conversely, if the team would have lost, if the team loses with that player, and the team would have lost without that player, then the player still wasn't useful in changing the outcome. And so how do you compute the Shapley value for a particular player? We sort of iterate through all possible combinations of the team, comparing the outcome when the player was present, and subtracting the outcome when the player is not present. If the outcome does not change, that difference, as you see in this visualization here, would then be 0, and so that marginal contribution becomes 0. And with this, you can sort of iterate through all possible combinations. You can see which combinations the player did contribute something, which ones the players didn't contribute something, and sum that all up, and you say that's the Shapley value or the marginal contribution of that player. So how does it apply to machine learning explainability and machine learning interpretability? Well, we can sort of do the same thing with machine learning features. You can sort of take a set of features, remove one, and see how the model's performance or prediction changes when you remove that feature. If the model's prediction does not change, then that feature wasn't really important. It really didn't do anything for that particular decision. On the other hand, if you remove that feature, you set that feature to 0 if it's a numerical feature, or you set it to the default category if it's a categorical feature, then that feature wasn't really useful. If the model's outcome did change, on the other hand, then that feature was useful. That changing that feature from its value to the null baseline value did change the outcome, then that feature has some marginal contribution to this output or that prediction. And so how do you do this in actual implementation? Well, this is a Python library called SHAP, short for Shapley values, created by Scott Lumberg, and that is very popular and is like probably the current standard for model explainability. And so one thing in this SHAP library is this tree SHAP algorithm. It's Shapley values for XGBoost or any sort of random forest or gradient boosted tree. And how tree SHAP works is that, well, instead of brute forcing all 2n possible combinations of the features, you can sort of take advantage of the hierarchical nature of the decision tree in order to test out different combinations of features. You can test out age, education, marital status, for example, and then also test out age, education, marital status, occupation, and work class, and see how the outcome changes there. And that allows you to infer age, education, marital status, occupation, and age, education, marital status, and work class. You can sort of approximate those intermediates quickly so you don't have to brute force all possible sub-combinations of the features. And so like I said, SHAP is probably the standard for model explainability at this point, and there have been a lot of like variations or frameworks built on top of SHAP, such as like baseline SHAP or conditional Shapley values. But in addition to feature importance for feature attribution, there's also this idea of how can we sort of create a value of data points using Shapley values. And so there's this one idea in algorithmic fairness of how do we compensate individuals for their data? The idea being that like Google and Facebook, they process all your data and they make lots of money off it. You should be able to get some of those you should be able to be earning some interest on that. If they're making money off your data, you should be rewarded for your data. There's a lot of like ethical and moral qualms about that. That won't get into this point, but it is an idea that's being discussed. Whether it's a good or bad idea is beyond the scope of this talk. So let's talk about the framework for this problem. If we want to create evaluation of data, the idea is that we have the training points, we have the data points in the training data set as players of the game, and given some learning algorithm, so given a random forest or given a neural network and some performance metrics such as accuracy on some holdout test data set, we want to optimize the performance metric given the data set. And the thing is here, the idea is that if you sort of take that training data set and you remove a particular point and the performance metrics changes, so if you remove a particular data point from the training data set and suddenly the accuracy on the test holdout data set drops significantly, well then that data point was very, very valuable. And where this might occur is in data sets that don't have equal representation of all the underlying features. So for example, when we talk about like computer vision problems, there have been a lot of issues where computer vision systems such as face recognition systems or face detection systems struggle at detecting black female faces compared to white male faces. So adding another black female face in your training data set may improve the performance of that model on the holdout test data set, and conversely, removing a black female data point face from your training data set may significantly drop your model's performance on some test holdout data set because there's less representation of black female faces in your training data now compared to white male faces where they're much more plentiful. And the goal behind this equitable evaluation of data framework proposed by Gorbani and Zhao in this 2019 paper of Data Shapley is that we want to compute the marginal contribution of each data point to the performance metric. And so how do they do this? They create this gradient Shapley algorithm. So you start with some random permutation of the training data. You update the model's parameters using stochastic gradient descent. So you optimize the model's parameters at by reading one data point at a time. And then you evaluate you evaluate the model at that stage on the holdout test data set. And you see how the change in performance occurred, and you attribute that to the data point. So each step of this process, you add another data point to train the model, you see how the model's performance changes, and you associate that as the contribution of the data point. And you sum this up, you reiterate this process until you sort of achieve convergence, and you can get this good estimate of the relative importance of each data point in achieving the changes in the performance metric. And so I think this is a cool idea, not just focusing on Shapley values for the features, but also how Shapley values can help us identify the value of data points. And this can help you think about beyond just how do you compensate individuals, but help you think about your data collection process. Like if certain data points of a certain type, for example, if black female faces have higher data Shapley contributions or data Shapley values, then you may want to get more black female faces for your training data set. It helps you address like data set bias problems, for example. Next, I want to talk about this idea of mechanism design. And now mechanism design is often called reverse game theory. Well, why is that? Well, the idea behind game theory is we start with some economic incentive structure, so we start with that payoff matrix, and then we try to find the optimal behavior for each agent. So you start with economic structures, find optimal behavior. Well, with mechanism design, you do the reverse. You want to start with the desired behavior for each agent, such as we want our agents to be truthful, we want our agents to be honest, we want our agents to act fairly. And then you try to find some incentive structure that induces this behavior. Well, how does this work? So let's consider this very famous problem in mechanism design called the cake cutting problem. So you have two people, Alice and Bob, because after all computer science problems involve people named Alice and Bob, and they're given a cake. And they must decide how to split the cake between themselves. And now we assume that both Alice and Bob prefer larger portions of the cake. They want to get as much cake as possible. So how can we cut the cake to appease them both? And formally, we said we want the cake allocation to be envy-free. We don't want Alice to want Bob's slice of cake more than she wants her own, and conversely, we don't want Bob to want Alice's slice of the cake more than he wants his own. So what's one thing we can do? So we want our players to be happy with their slice, and we don't want them to be jealous of each other. How can we achieve this? Well, here's a possible solution. So here's the mechanism for how we induce this. Alice gets to cut the cake into two proportions, and then Bob gets to choose which proportion he wants. So assuming Alice is rational, and I have an asterisk here because I mean rational is defined by rational choice theory, which means she's like mathematically optimal and self-interested, she will realize if she cuts the cake unevenly, so for example, she cuts the cake into like a 70-30 portion, Bob can always take the larger portion of the cake. So if she cuts the cake 70-30, Bob takes the 70, she's left with the 30, and thus Alice is unhappy because she's jealous of Bob's portion. So in order to maximize her own portion, Alice has to cut the cake 50-50. That way she gets 50% of the cake, Bob gets 50% of the cake, she's happy, she's got the maximum amount she can get, and she won't be jealous of Bob's proportion because Bob's proportion is like equal to hers. And thus, this framework results in an optimal allocation that is both proportional, it's fair, and that they both get half the cake, and it's envy-free in that neither prefers the other's slice of cake. Strictly prefers, so like, they're not jealous of each other. And this is a fun theoretical problem, but it actually has cool applications to this real world. So there's this like not-for-profit tool called Split It, which uses this idea of the cake cutting problem and is created by algorithmic game theory professors out of Carnegie Mellon University to use this idea of this cake cutting problem and mechanism design to do fair divisions of goods. So if you're a set of roommates trying to decide how to like split rent evenly among you based on like the different rooms in the apartment or household, you can use Split It. If you're trying to divide up a set of goods, say recipients of a will, you can use Split It to divide up the goods fairly such that everyone is happy and no one is jealous of each other. And so I think this is a cool tool for showing the connection between like theoretical computer science and economics, but applying it to a common real world problem. And in addition to talking about how we can apply mechanism to design to real world problems, I think one of the biggest contributions of mechanism design is this idea of how do we design markets for the exchange economy. So rather than paying money for goods, it's sort of like how do you barter with each other? I give you A, you give me B. And most notably, Alvin Roth won the 2012 Nobel Prize in Economics for this work, specifically in the design of kidney exchange markets. So how do kidney exchange markets work? Well, kidney exchange markets refer to kidney donations. You want to have a set of donors and you have a set of recipients. And we want to take kidneys from the donors and match them to the proper recipients. So how do you do this? You construct a bipartite graph connecting a donor D to a recipient R if they have a blood type compatibility. So one thing about kidney donations, or any organ donation in general, is that you have to take into consideration blood types. With blood types, there are those universal donors, blood O type negative, and those universal receivers, blood type AB positive. And the heuristic for how we make the optimal number of matches is that we want to be efficient with our matches as much as possible. We don't want to be greedy. So there's no point in matching a universal donor on a universal receiver. A universal donor can give to anyone, and a universal receiver can take from anyone. So we really don't want to waste our donations on those, because the universal donor could give to someone who has a much bigger restriction, and the universal receiver can receive from anyone. And so what Alvin Roth's work shows is they proved a way to get the maximal, they produced an algorithm or a mechanism for producing the maximal number of matchings in this kidney exchange graph. And this is actually what's commonly used now across hospitals in order to maximize the number of kidney donations, thus resulting in saving millions of people's lives, or thousands to millions of people's lives each year. So I think this is one way to show how you can use mechanism design to achieve socially good outcomes. And that leads to this idea of this mechanism design for social good movement. This emerging area of research was founded by Radit Abibi, who is pictured here. She was a graduate student at Harvard University at the time, and I believe now she is a professor at UC Berkeley or some UC school. And she's also the co-founder in the Black and AI movement. And so how does mechanism design for social good work? Well, it's a research initiative to use ideas from theoretical computer science and algorithm design, mathematical optimization, and economics in order to create solutions and markets and mechanisms to help underserved and marginalized communities. And I think the key contribution of the mechanism design for social good movement is that many existing data science for machine social good or AI for social good initiatives often apply existing algorithms to the problems with high societal impact. So we're taking existing algorithms and applying them to these types of societal or humanitarian problems. The goal of this mechanism design for social good research is to create new mathematical and computational frameworks or algorithms for optimizing resource allocation or improving information access to these marginalized communities. And I think this is important because I think there's a lot of talk about how do we achieve fairness and reduce bias in machine learning models, which really just treats the symptoms. And I think mechanism design is really good at sort of how we address the underlying causes. Yes, you can devise a model and make it more fair according to some algorithmic fairness metric, but you're really just treating the symptoms, which is the model performance, but you're not changing the underlying data. With mechanism design for social good, by creating new algorithms and new computational frameworks, you are now addressing the underlying issues. You're changing the underlying, you're creating markets or structures in order to change the underlying data. And I think that's important. So let's talk about one example of mechanism design for social good, and this is a paper published by Radit Abibi on how do you allocate income subsidies to households that are at risk of income shocks. And so what this means is if you have households with low incomes, they have different susceptibility to income shocks. So for example, if you are barely struggling to make rent and all of a sudden you get hit with an unexpected medical bill because there's a giant global pandemic going on, or you get into a car accident and you're hit with this $500 maintenance bill or mechanic bill, then could be very close to the verge of bankruptcy. And the goal with this research is we want to allocate a set of income subsidies to these households such that we reduce the risk that any of these households experience financial ruin. We reduce the risk that they experience bankruptcy. And how this works is the authors use this idea from ruin probabilities from finance and algorithmic trading optimization to create this framework to minimize the likelihood that any household experiences financial ruin. So how do they do this? Like I said, here's the mathematical formula here. Essentially, the idea is they model the household's starting income. They model the income flow, so how much model paychecks and other income sources. But then they also model the probability of income shocks. They model the frequency of income shocks, so how often does a household experience income shocks, and then also the size of those income shocks. You get hit with very large bills very often, unexpected bills very often, or you get hit with a rare small bill every blue moon, once in a blue moon. And so what's the problem formulation with this? So each household I starts with some initial income reserve U of I. At each time step t, the household receives some net income C sub I. However, the households also randomly experience income shocks. They get hit with medical bills. They get hit with repair bills during each of these time steps. And at each time Ri of t, so basically the household's outcome at time t, we never want the household's total income to drop below 0. And if you look at this and think about it for a few seconds, it has a lot of connections to random walks. You start with some initial step, you go up, you might go down if you experience some income shock. And the idea is to always stay above that line, y equals 0. You never want to go into a negative income value. So how do we solve this problem? So essentially the problem is how do we allocate those income subsidies such that the household's random walk always stays above 0, or is reduced the likelihood that the household's random walk never goes below 0. Well, there's two ways we can think about allocating these income subsidies. We have some fixed budget B for allocating income subsidies, and we want to give a subsidy x of I to each household, such that the sum of x of I equals B. Well, there's two different goals that we have in mind when we allocate subsidies. The first goal, or first objective, is this min-sum objective. In this objective, we say that we can't save all the households. That some of them will have to experience financial ruin, but we want to save as many households as we can. So how do we do this? We sort of give each household a weight, representing the social cost of ruin. And in this formulation, we sort of want to minimize the expected social cost of ruin by the value of the household times the probability of it experiencing financial ruin if we're given some income subsidy. And the solution to when you have this objective function that you're trying to solve for is it can be approximated using the knapsack algorithm. So how does it relate to the knapsack algorithm? It's well, you can think about the value of the household. The value of the household is sort of the societal weight. How valuable is it to save the household is its societal weight, and the weight of the household is sort of the income subsidy. So it's better to save multiple less valuable households using smaller subsidies rather than just picking one big household and using all your income subsidies to save one household that has a lot of societal weight. On the other hand, we can have this min-max objective. In this objective, we want to keep the worst ruin probability experienced by any household as low as possible. So in this objective, or this goal of min-max, we want to save all the households. And how we do this, we sort of view this as this min-max problem. We basically find what is the worst probability. So what is the household with the highest likelihood of experiencing financial ruin, and minimize that. Keep that as low as possible. So even the worst case is still pretty good. And so how do you find a solution to this formulation, this min-max problem? Well, it can be approximated using a modified binary search. Essentially, you guess some initial solution, solution P. If you find it's infeasible, adjust down. If you find it is feasible, adjust up. Keep doing that, do a binary search, and you can eventually converge to what is the closest approximation to the optimal solution to this min-max problem. And so I really like this paper because they show a way to connect theoretical computer science and mathematical optimization to a problem that has a very high societal impact. This is a framework of allocating income subsidies that can be very useful to government agencies that work with low-income households. And this can be used to help these households avoid financial destitution, especially during these times where people are struggling to find work, they're very struggling to pay rent, and they're struggling to afford food. And this could be a way to help these households have these income subsidies such that they don't have to experience bankruptcy or some disastrous outcome. And so that's really it from this talk. I hope here's the papers I referenced. The first paper is the SHAP paper itself, a unified approach to interpreting model predictions by Scott Lemberg. Next is the Data Shapley paper. It talks about how do you value data points in a training data set. The Kidney Exchange paper by Alvin Roth. And finally, the subsidy allocation in the presence of income shocks by Radita Beebe and other researchers at Cornell University. In addition, here's some further resources for anyone interested in learning more about game theory, mechanism design, and the way you can apply these game theory mathematical optimization problems to socially good outcomes. So that's it for my talk, and I really hope you enjoyed that.